Okay, so now we're going to talk about the mean, okay, and the variance of a uniform distribution. Both of them are required to know, so you need to know how to do the derivation, okay? In here, I will give some parts of the derivation, and then with the details that you can check it out later, or you can check out the textbook for further detail, okay? So we talked about the uniform distribution is PDF, right? And it's CDF. So now to get the mean, okay, and we know how also like from the previous 2 videos ago, you have seen how to get the expectation and the variance of a continuous random variable. So we are really just following that result, okay, and trying to do it step by step. So the expected value, okay, of a uniform random variable between alpha and beta is actually just half of the sum. Okay? Not surprisingly, right? Because it's uniform, it's equally likely everywhere, and then expectation is at the middle point. Okay, so how to show that? So the expectation, all right, of the random variable, we know that, well, I skipped the general step. If you remember, like the general step is always negative infinity to positive infinity, and then x, fx, dx, right? We can always start with that, okay? But now we can, if you get familiar with this, you can jump to the next step. Now we're integrating from this should be, yeah, I think this should be alpha. Sorry about the typo, okay? So alpha from alpha to beta, okay, because the PDF is only non-negative there, right? It's the constant over there. If it's outside this range, it's going to be 0, so we don't really care about them. So we're integrating x times fx, because fx is 1. So fx, let me just write it out over here. 1 over beta minus alpha, right? When x is between beta and alpha, and then 0 otherwise, okay? So that's why we are doing, so x, right, times 1 over beta minus alpha, right? And then we do dx. Okay, so then the rest is, again, calculus 2. Okay, so just do it really carefully. Remember that beta and alpha, all of this are constant because the integration is only about x. Okay, so here we're going to do ax squared divided by 2 times beta minus alpha, and then we're doing the integration from alpha to beta, take the difference. So eventually you're going to arrive at alpha plus beta divided by 2 to be the mean. Okay, so mathematically you see how this works, so that's good. But also intuitively, like I said, because it's equally likely to be anywhere between alpha and beta, so it's not surprising, right? The mean is at the middle point. Okay. So the variance, okay, the variance expression is slightly more complicated, maybe not so intuitive. I probably wouldn't be able to give a good intuitive understanding here anyway, but we can always show it mathematically, okay? So this, again, is required, so you need to know how to do it, okay? And variance, just so you know, we have variance is typically obtained by expectation of x squared minus the square of the expectation, okay? So we follow that, okay? Follow that mean, okay, so I would just also remind us that the expectation of x earlier on the previous slide, we have shown it to be alpha plus beta divided by 2. Okay, so keep those in mind. Okay, I'm going to show the step down here. Okay, so first one is to get the expectation of x squared. Okay, and then that, just so you know, expectation of x squared for the generic method, because this is a function of a random variable, right? So for a continuous random variable, we do x squared, right? And then fx dx. Okay. So here we have x squared, right, divided by beta minus alpha, because 1 minus beta and alpha is fx itself. Okay, again, we are narrowed down to integration from, so again, sorry about that, this should be alpha, from alpha to beta here as well. Okay, and then do the math, do it carefully, step by step, then you're going to arrive at this as the expectation of the x squared. Okay, and then the next step is going through this step just more carefully as well. You will see that you are doing the expectation of x squared minus the square of the expectation. And then I know this is quite involved, but if you do it step by step and then do it right, you should arrive at this point. Okay, so we're utilizing the result earlier that we have derived already. Okay, and then in this part, the new derivation is about the expectation of x squared. Okay, that involves a integration, okay, of power of x. So really just be really careful about the steps and then about the math as well. All right, so with all that, let's look at some application, okay, of doing probability calculation for a uniform distribution. So another thing, okay, we can always, like I said, you can always integrate, right? Do integration to get the probability of X in a particular range, okay? But for a uniform, okay, so this just to refresh our memory one more time, this is what we first used, right, to define a continuous random variable, right? If I have the PDF of it, if I want to know the probability of X falling into a particular range like B, like a set, then I'm integrating the PDF over that set. Okay, so that's the general result. Okay, but then for a continuous uniform, okay, uniform random variable in particular, you will see that, well, because it's equally likely, the fx is equally likely everywhere. So it turns out that the probability, if I want to know the probability of X in a particular range, like B, is actually just going to be the length of B divided by beta minus alpha. Okay, so this might sound a little bit vague, but let's look at example that, like I said, you can always do the integration to get the probability, but maybe it's also easier if you just think about the length. So for example, I want to take a bus to the airport this afternoon. Okay, the bus arrives at my nearest bus stop at a 10-minute interval. Okay, starting at 4 p.m. Sorry about the typo. Okay, this is interval. Okay, sorry about that. And starting at 4 p.m. Suppose I arrive at the bus stop at a time uniformly distributed between 4 and 5. What's the probability that I will have to wait for more than 7 minutes? Okay. All right, so let's start with defining my random variable. Okay, my random variable, let's just say it's X. Okay, X is the time I arrive at the bus stop. Okay, and if I think about it in terms of minutes, okay, it's going to be a uniform random variable between 0 and 60, okay, in terms of minutes, okay? And then in particular, the question told us that the bus is gonna arrive at a 10-minute interval starting at 4, okay? So the time that the bus is gonna arrive, right, is gonna be at 0, well, yeah, 0, and then 10, 20, 30, 40, 50, and 60, okay? So the interval, sorry about that, interval, okay, of my arriving time such that I have to wait for more than 7 minutes actually becomes, if I arrive anywhere between 0 and 3 minutes, okay, then I have to wait for more than 3 minutes for the next bus to arrive, right? Or between 10 to 13, right? Or 20 to 23, 30 to 33, 40 to 43, and then 50 to 53. Okay, so all of this. And since they're discrete, right, from each other, so anytime, so my B, this particular set that I'm working with, is actually the union of all of this, okay? And then in particular, because it's a uniform random variable, right? So pretty much we know that if we add up, right, all of the length over here, like we have a 3 here, another 3, another 3, so we have, I think, 6 3s in total, right? So if we follow this result, okay, if I know the length of B, okay, then I will be able to do the probability calculation pretty quickly. Okay, so here, if I'm doing that, then I will get 3 times 6, okay, divided by 60, because that's the length, okay, of the overall interval in the first place. So I'm gonna get 30%. Okay, so not surprisingly, actually, right, because it's coming in every 10 minutes, and then I'm asking about waiting for more than 7 minutes. So the probability of doing that is like 1 minus 7 over 10 anyway. But here we're showing it mathematically of how that can work. Okay, like I said, you can always do the integration one by one, but of course it's a little bit tedious, and that's why we're introducing this handy result. Okay. Alrighty, so recap, okay, expectation for continuous random variables, okay, of X, okay, if it has a function of it, then you are able to get the expectation, and then of course the expectation of the function itself as well. Okay, so those are for the continuous random variable. Okay, and then we talked about the uniform distribution. Okay, we talked about its PDF, its CDF, its mean, and its variance. So all of them are going to become really handy. Okay, and we also saw a really handy outcome just now, or method just now, how you're able to get the probability of a particular event if you're able to get the length of the event B, right, and then divided by beta minus alpha, you're able to get that from a uniform distribution pretty quickly as well.